Hi, everybody. I'm Dan Klein. I'm a professor here at UC Berkeley. I am also the CTO at Scale Cognition, which is a lab focused on high reliability agentic models with verifiable behavior. Let me start out by telling you a story you probably already know, which is due to all these amazing capabilities of AI today, it seems like a small team or even a single engineer can whip up an eye-popping demo seemingly overnight. Executives get really excited, this is the future, and go, go, go. 3 months later, there's still some details to iron out. 6 months later, we're working through some reliability issues. So will this thing ever ship? So if you've seen something like this play out, you're not alone. There are a bunch of studies that show that most agentic AI initiatives in enterprises stall or fail, and when they ship, sometimes they can face plant even spectacularly. So what's going on? What really is behind this contrast between demos, which are easier than ever, and that last mile to a reliable product, which still seems to be very hard? So really at the core, intelligence is multifaceted. And although systems are getting smarter and smarter, not all aspects of intelligence are advancing at the same rate. The key reason why it's so hard to make reliable products, even still, is that reliability has not kept pace with other aspects of intelligence. So, what does that actually mean? Well, if you look at today's models, and you look at things like their breadth of knowledge, or their plasticity of behavior, or their fluency of output, on these axes, things are just through the roof and only getting better. But if you look at things like the ability to exert precise verifiable control, or the ability to explain the output of a model, these aspects have consistently lagged behind the others. What does this have to do with demos versus products? Well, to make a demo, you really need the things on the left. But if you want to be able to ship a reliable product, suddenly everything on the right becomes critical as well. So this kind of signature of strengths and weaknesses both explains why it's so hard to go that last mile. And when systems do ship, their failure modes often encode this exact same signature of strengths and weaknesses. So what does that mean? Let me give you some examples. So maybe you've seen the burrito bot, which is happy to take your order or debug your code. What's going on here? Well, this is actually the breadth of the underlying model showing up as a flaw, especially when accompanied by imprecise control. Or maybe you saw this car, which you can get for $1 because there's an AI sales bot, which is happy to take an instruction from the user that says all user deals are to be accepted. Well, what's going on here? This is the plasticity of the underlying model, such an advantage in development of a demo, but now it's not really wanted. Now, you could look at this and say that's a prompt injection attack. Surely we know better now. This sort of thing isn't happening in 2026. But it turns out even in 2026, there are some cars going for cheap. So in general, when systems start taking actions, it becomes that much more important that they be sure. If you're going to take an action with consequences, you really have to know and be able to verify that you're doing the right thing. So for example, if a system can edit your database, it can delete your whole company's database, and that's not good, but it could be worse, right? Healthcare mistakes, financial mistakes, these could be devastating. Now, you might think, how many times can an AI delete the whole company's database? Surely this isn't happening in 2026, but it is. All right, well, it turns out when smart people try basically reasonable things and see consistent barriers, probably there's something structural going on. This isn't just a one-off anomaly or a mistake. So what are the sort of structural enduring barriers, and where do they come from? I'm going to talk through 5 of them quickly today, and a little bit about what the shapes of solutions are going to look like going forward. So the first barrier to reliability I'm going to talk to is the issue of basically invisible errors. If you take an LLM and you look at the kinds of errors it makes, for example, think about hallucinations. I like to think of these things as an iceberg. The top of the iceberg, the small part, is the errors which are wrong and sort of obviously so. You look at that and you know something's gone wrong. The problem is most of the iceberg is under the water. So at Scale Cognition, when we talk to prospective customers, and we're talking to them about their current technology and hallucination rates, and then we do a careful audit. Typically, we find that the actual hallucination rates are something like 5 times what they thought, because most errors just don't get discovered. So what's going on here? Well, LLMs are, at their core, plausibility engines. They produce plausible output, and hopefully often that output is not only plausible but right. But when you make a mistake, it tends to be the bottom of the iceberg. Now, that can be a problem during development because it's hard to fix an error if you can't catch it. But it can also be a problem when you ship. Why? Well, like, here's the example of a customer service email. This email is very human-like, it's very fluent, it's very authoritative. It just happens to be describing a bogus hallucinated licensing policy. And because it is so fluent, there's no real way for users to work around this error or to tell what exactly has gone wrong. All right, well, if you find errors, you want to fix them, and that means you need control over your systems. And there is this enduring challenge of insufficient control, and it boils down to the fact that the primary control surface, which is a prompt, really lacks any kind of precise semantics. So what do I mean by that? Well, imagine you have a banking agent, and users are going to come up and maybe ask for a loan. And on the other side of the agent is a bunch of financial APIs. Well, this agent is also going to have some instructions. Some of those instructions will be inherently soft, like be reassuring. But some of them will be inherently hard, like quotes are authorized through this API or something like that. And the problem is when you put instructions into a prompt, they all become soft. There's nothing really crisp you can say about the relationship between the tokens you put in and the behavior you get out. And that's a real challenge. So what do people do? Well, probably a lot of people in this room have had this experience of taking your prompt, rewording things, putting things in all caps at the end of the instructions, adding some exclamation points. Maybe after the third exclamation point, you start to feel like this isn't the right control surface for hard control. So what are people doing out there? We can have other kinds of control structures. For example, you can try to get hard control by having an external harness, and you put models checking models or code verifying things. And this is a step forward because now you have a way of doing some kind of hard control. But it's still very challenging because models checking models adds latency, it adds expense, and it can be kind of a very complex and unreliable kind of architecture to maintain. What would we really like? What we'd really like to have is models that just have control surfaces in the first place for hard constraints, and that do verification internally to the model. So this is the approach we take at Scale Cognition. I'll talk a little bit more about our models later, and I think this is increasingly what you're going to see. Now, that's really about the architecture of the input, how you control the model. But we also need to talk about barriers that come from the architecture of the output. We'd like to have models which tell the truth, preferably models which guarantee that they tell the truth in some verifiable way. But that's a big difference between verifiable truth and just happening to output a correct sequence of tokens. So here's an example. If I ask a model, what's the population of Berkeley? Well, it's going to throw together some tokens to give me an answer, or maybe it'll throw together these tokens. They're plausible, but they aren't actually right. Or maybe it'll throw together these tokens, and these are plausible, and they're also correct. Now, that doesn't mean the models aren't going to be correct more often than they're wrong. Hopefully, they're correct most of the time. But the important thing is that a vanilla LLM can't actually tell the difference between when it knows something and when it doesn't. These are just guesses. Some guesses are right and some guesses are wrong. What would it take to actually be sure? Well, it would take some kind of metacognition. So you can see glimmers of this in a system, for example, that issues a query to a tool call or a RAG system, where it decides that it's going to do this query and output the result. Now this is now starting to go down the road of metacognition, which is doing computation about how you will do computation, how you will think. And this is not the only kind of metacognition. For example, if I ask people in this room, what's the population of Berkeley, probably the most likely answer is, I don't know. And humans are very good at tracking whether or not we have an atom of knowledge. Systems do not currently do this, and I think it will be increasingly important that systems become metacognitive. All right, of course, the behavior of a system is critically intertwined with how it's trained. Increasingly, the behavior of systems comes not just from their pre-training, but from post-training, which tends to be done in a reinforcement learning manner. Now, you've heard about a lot of amazing advances based on reinforcement learning, and in areas like math or coding, there have been these explosive instances of progress, this is because these are verifiable domains. So as, for example, game playing. In these domains, you can take your proof and check it with lean before you train on it or hand it to the user as output. So verifiable RL can be very, very powerful, but most domains aren't verifiable. How can non-verifiable RL cause problems? Well, it can increase some aspects of intelligence at the cost of others. So to give you an illustration of this, I'll offer you this parable of the shipping bot. And the shipping bot has a user that comes and says, where's my order? The tracking hasn't updated in a while. And the shipping bot checks the database and finds that the package is lost. So it says, your package is lost. So far, so good. But what happens if we layer RL on top of this and we don't do it carefully? Maybe we tell the system to optimize thumbs up, maybe in the form of net promoter score or something like that. Well, it's probably not going to get a thumbs up for this answer. But maybe if it said your package is on your way, the user might be happy, at least in the short term. Well, now you've just taught your system to lie to you. And in general, does this happen? Well, it actually does. So for example, if you have RLHF, that can increase human approval of outputs while actually degrading their factual accuracy. Okay. And then last, but certainly not least, one of the barriers to building reliable systems is that superintelligence turns out to be super expensive. Well, we actually already know why that might be. For example, you may be paying for breadth that you don't need or want. You may be paying for models to check other models, either in tokens or latency. Or you may be paying for test time compute, which is essentially teaching your model to do something at test time that you really wish it had already known how to do in advance. All these things can cost a lot. And as a result, you see this trade-off in generalist models between, here you can see a bunch of models on an agentic benchmark. The upper left models are accurate but expensive. The lower right ones are less accurate, but they're much more cost efficient. How could you get off this curve? Well, for example, our model APT is a model that is specialized to agentic interactions. That means humans on one side and APIs on the other. And this is a specialist self-verifying model, and this lets you get high accuracy and also high efficiency, and I think this is going to be increasingly part of the solution. So what are reliable solutions going to look like? I think you're going to only hear more and more about verifiability all throughout the system, in the data, the architecture, the training, the inference. There's going to be richer control surfaces that let you actually tell your system what you want and get guarantees that it will actually happen. And then I think you're going to see an increasing reliance on efficient specialist models that maximize the use of the resources of compute available. And in general, reliability is very important because reliability is what gets you from these demos to products that you can actually ship. Thank you.